In this video, I'll be going over the Unit 1 assignment that is also on code.org, following up on representing images from black and white, but now moving on to how we can represent images on a computer in color. So again, this is going to involve work on code.org, and if you have this open, you can just simply click on this link and it will take you right to Lesson 8. So Lesson 8 is talking about representing color images using binary. So in the last lesson, we used 1 bit per pixel, which meant we only had 2 choices for a pixel, either black, which we represented as 0, which we can think of as being off, a light being off, or we could represent the color white with the number 1, which we can think of as having a light on. So in this lesson, we're going to talk about how we can increase the number of bits per pixel so that we can have a greater variety of color. So we're going to start out with using 3 bits for each pixel. So if we use 3 bits for each pixel, we can use the RGB model. So the RGB model is red, green, and blue. So we can think of this as having 3 different switches that has a red light, a green light, and a blue light. So if we just have red on and green and blue are off, that's just going to result in the color red. So we can represent that with the binary number 1, 0, 0. Red is on, green is off, blue is off. We could also make green by only turning on the green bit and having the red and blue bits off. So this would be represented by the binary number 0, 1, 0. And they don't have blue on here, but we could probably figure that out. If we wanted just the color blue, we could have the blue switch on, or the blue bit on, and red and green off. And so we could represent that by 0, 0, 1, where this first 0 is the red bit, the second bit is the green, and the third bit is the blue. There are some other colors that we can create by combining green and blue, green and red, red and blue, etc. And we're actually going to figure out how to do that. So as we know, if we have 3 bits, we can actually have 8 different choices of color. That's because we can represent 8 different values in 3 bits, the numbers 0 through 7. So for instance, we could have 0 represented by 0, 0, 0, and we know that the binary number 1, 1, 1 equals 7 in base 10 because this is our 1 spot, this is our 2 spot, and this is our 4 spot, and if we add 4 plus 2 plus 1, that is 6. Or sorry, that is 7. So again, we have the numbers 0 through 7, so that's 8 possible different combinations. So let's go ahead and see how we can use these binary representations to create 8 different colors. I'm going to click on Continue. And you can watch this video at your leisure. It's about 4 minutes and it talks about the color pixelation widget, but I'll kind of be guiding you through this, so that might not be necessary. Alright, so I'm going to start this over. And when you start out this exercise, they give you 2 colors already, but you'll notice that there's a lot of numbers in here for just 2 colors. Remember that each of these colors is represented by just 3 bits, and you see a lot more than 3 bits in here. So let's break this down and figure out what's actually being represented here. So you'll notice that the first line has an 8-bit number. This 8-bit number represents the image width. And if you see over here, this width is represented by 1 byte. And what's the same as 1 byte? Well, that is 8 bits. So we know that this first 8-bit number, or this 1 byte number, represents the width. If we translate this binary number to decimal, for instance, looking at the place values, so this is the 1s, this is the 2s, and this is the 4s, and the rest of these aren't really relevant because these are all zeros anyway, we know that this number is 4 in base 10. So you'll also see that up here. I can also move this slider, and you'll notice that the numbers in down here actually change with it. I'm going to set that back to 4. And so we know that the width of this image is 4, and we see 4 pixels going across here. And you could probably guess that this next 8-bit number, or 1 byte, remember 8 bits is 1 byte, represents the height. And so this number translates to 2. And so this is saying my height is 2 pixels high. And so we see that represented there as well, and we also see the number 2 right here. The next 8-bit number is bits per pixel. So that's how many bits is used in order to encode the color for a pixel. So here we see this 8-bit number is going to translate to 3, which is what we see up here as well. So that's why we have these extra bits up here. It's for the width, height, and pixel, and they will automatically get changed and added to this screen as you move the sliders. For this exercise, we don't want to manipulate the sliders at all because we do want to create 8 separate numbers, or 8 separate colors. So like I said, the first 2 colors are done for us. So you'll notice that this first 3-bit number is going to make the color red. And remember, that's because we're using the RGB model. So the first bit represents red. And so since red is 1, that means that bit is on. So we're getting that red color. Green and blue are off, which means that we only have the red color, and that's why we see a pure red color right here. The next number that we see is 0, 1, 0. So again, looking at that RGB model, we see that only the green bit is on, and that's why we see a pure green color here. So next what we want to do is we want to create pure blue. So I only want the blue bit on for that. So I'm going to enter 0, 0, 1 so that only the blue bit is on. And there I see blue. But remember, we have 5 more colors that we can create for a total of 8 colors. So there's more combinations that we can create. I wonder what will happen if I turn all of the bits off. I think this is the equivalent of turning all the lights off, and so maybe it will be black. Okay, so that we can confirm that turning off all the bits will be black. What's the opposite of black? Well, it's white. So if I turn on all of my bits at once, I can expect to see the color white. There we have it. Now, the remaining ones we might be wondering, so what happens if I turn on the red and the blue bits? So again, talking about the RGB model, what happens if I turn red on and blue on, but I leave green off? Well, logically, I know if I took art, or even if I've drawn with crayons before as a kid, when you mix red and blue together, it's kind of a purpley color. But with light, it's a little bit different, because remember, this is a representation on the computer, and on a computer monitor, colors are represented by shades of light. And so if I have a red light color and a blue light color, when they combine, it turns out that it's a little bit more pink than purple. So I'm going to put that on there, and you can see that it's more of a magenta color. What other colors can I combine? Let's see, I can also do green and blue. So now again, talking about the RGB model, this is going to look like red is off, green is on, and blue is on. So when I combine these 2 colors, it's going to make this really bright blue called cyan. So let's see what that looks like. There's cyan. And then finally, the only other color combination that I have not done is green and red. So again, looking at the RGB model, that's going to look like having red on, green on, and blue off. When I combine these 2 colors, I'm going to make a yellow color. So let's see what that shade looks like. And there's my yellow. So in using 3 bits per pixel with the RGB model means that we can create these 8 different colors. But in reality, we've evolved beyond this particular model of only using 3 bits per pixel. And today we can see that we can actually represent trillions of colors, although that would take some time to go through each of them. So instead of doing that, we're going to see what we can make with a 4-bit per pixel model on the next one. Okay, so now we are going to actually use 6 bits per pixel because now we're using 2 bits for each color of light. So before we had just 1 bit for red, 1 bit for green, and 1 bit for blue. But what happens when we expand this to 2 bits per color? So if we have 2 bits per color, that means we're going to have 6 bits total for each pixel. And this means that we can have a wider variety of colors. So instead of only having 8 different colors, now we can have up to, let's see, so we have 6 bits. So if we are using 6 bits total for each pixel, that means that we could now create 2 to the 6 different colors. This means that we can make 64 colors. So we're not going to make all 64. Instead, we are going to generate a gradient of each of our primary colors. And when I refer to primary colors, when I'm talking about computers, I'm talking about red, green, and blue. So we're going to create gradients of red, green, and blue on the next exercise. Once again, there is a video that you may want to watch, but I will be walking you through the assignment. So I'm going to go ahead and reset this. And to start out, they give you a gradient of red. So once again, these first 3 bytes represent the width, height, and the bits per pixel. So now you can see that we're working with 6 bits per pixel instead of 3. So now what we want to do is we want to kind of examine this first line to see what is actually happening so that we can then generalize these patterns to create a gradient of green and blue. So as we see with this first one, all of the bits are off, which means that we're going to get black. But if we look at the next bit, let's kind of split this up. So again, we know that we are now following this format where we have 2 bits for red, 2 bits for green, and 2 bits for blue. So I'm splitting these up. So I know that this is going to represent my red, this is going to represent my green, and this is going to represent my blue. So this means my green and blue bits are completely off. They have no effect on the color that I see on this screen, on this next pixel. However, the red color has a value of 1. So in binary, this is 1 because only the only bit that is on is in the 1 spot. So I'm going to get this darker color of red. If I go to the next value, I can see that still my green and blue bits are off, but now my red has increased to binary number 2 because I know that this is my 1 spot and this is my 2 spot, so this binary number is 2. So I can expect to see more red, or in other words, a brighter red color. So now I kind of see this color of red that's kind of a medium red. It's in between this dark red and this brighter red here. So if I go ahead and go to the last value here, I can see that again my green and blue bits are still off, so they have no impact on the color that I see in this pixel. And now my red is set to maximum, the maximum value for 2 bits. And that maximum value is going to be 3. And once again, if I look at the place values, this is my 1 spot, this is my 2 spot. Both of those bits are on, so I'm going to add 2 plus 1, which is going to be 3. So now I see a super bright red that is brighter than the preceding colors before it. Okay, so now we're going to use this pattern to create a gradient for green. So we're going to start this off with pure black, which is going to be all of the bits off. The next thing I want to do is I want to make the darkest green. So I know that my model is RGB with 2 pixels for red, 2 bits for red, 2 bits for green, and 2 bits for blue. In this case, I only want green color, so I'm going to turn my red and my blue bits off. And now I want to have the smallest value of green that is not 0. So that's going to be the binary number 1, which, is 0, 1. So this is going to be the first value that I want to plug in to my widget here. So I'm going to go ahead and put 0, 0, 0, 1, 0, 0, and now I see a very dark green. The next value that I want to create is going to have a little bit of a higher value in my green bits here. So I started off at 1. Now I want to increase my green bit to binary number 2, which is going to be 1, 0. So now I'm going to go ahead and put in my next position here, 0, 0, 1, 0, 0, 0, and that should give me a medium green color. And there's my medium green color. Finally, I'm going to increase the green bit value to the maximum, which is going to be 3. And again, 3 in binary is 1, 1. So the next value I'm going to put is going to be 0, 0, 1, 1, 0, 0. And that should be my bright green. And there it is. So last we're going to work on the blue gradient. As always, we're going to start off with the color black. And now we notice that since we're on blue, and then we have 2 bits per color, we're always going to have the red bits off and the green bits off. So we're always going to start with 0, 0, 0, 0. And this time blue is going to change. So for the first value, we're going to start at 1. And then for the next value, we're going to do the same thing with the red and green bits off. And now we're going to increase the amount of blue. So last time it was 1. Now we want to put binary number 2, which is 1, 0. And then finally, again, we're going to have red and green off. We want to put the maximum possible blue value, which is going to be 3, which in binary is 1, 1. And there's our brightest blue that we can represent using 2 bits to represent that color. So next we're going to go ahead and proceed to the next task, which is using now 9 bits per pixel. So now we're going to have an even wider variety of colors with this. So that's going to be 2 to the 9, which is 256 different colors. Seems like a lot, but that's still very few considering how many we can actually represent today on a computer, which again is in the trillions. So once again, I'm going to go ahead and start this over. And again, we're not going to be making all of those colors. We're just going to create the gradient as we did in the last exercise. So again, you can see that we're starting with black and we're working ourselves up to the brightest color of red in this instance. So if I split these up, we can begin to see how this works. And it's very similar to what we saw last time, except now we're using 3 bits per color in each pixel. So this time we have 3 bits for red, 3 bits for green, and 3 bits for blue. So now the maximum amount that we can represent for any color is going to be 7. So each color value can be represented anywhere in between 0 and 7. Notice that if all of our pixels are off, once again we get black. And for this value, we see that green and blue are completely off, but red has a value of 1, and so we see this really dark red that might not even show up as red on your screen. In fact, it looks kind of in between black and brown to me on mine. And then as we move on to the next value, we can see that, again, our green and blue values are off, and red this time is 2, and now we see something like a deep maroon here. And this proceeds all the way to the right, so increasing red by 1 each time. So here red is 3, red is 4, red is 5, red is 6, and here red is at its maximum value of 7, where you see it at its brightest. So we're going to follow this 3-bit per color pattern to create gradients for green and blue as well. Again, we're going to start off with black, so that means that we're going to be turning all of those color bits off. So we're going to have 0 for red, 0 for green, and 0 for blue. Now that we're dealing with green for this row, if we take a look at our RGB model, this time we have 3 values per color. So we know that we want to, in this case, only have a very minimum value for green, but red and blue should be off in this case. So we know that there's going to be 0s for red and 0s for those last 3 bits for blue. So now I want to increase green by 1, so I want the binary number 1, which is going to be 0, 0, 1 in 3 bits, and we can plug that in to the widget. And now we see a very dark green that almost looks black. And then as we proceed to the right, we're going to be increasing the green value by 1, but keeping red and blue completely off. So for my next green bit, I want the binary number 2, and in 3 bits, that's going to be 0, 1, 0. And then again, blue is completely off. Now again, I'm going to have my red bits completely off. And now, since my last green value was 2, I want to increase that now to binary 3, which is in 3 bits is going to be 0, 1, 1. And then finally, our blue value is going to be completely off as well. Okay, for the next one, again, our red values are off. And now I want my green to be, it was 3, so now I want it to be 4. So if I remember my place values in binary, the smallest bit is going to be my 1 spot. Then going up, it's always going to double as I go higher, right? So the next is 2 spots and then 4 spots. So if I want to make the binary number 4, we're just going to turn on that bit to the left and have these other 2 off. So binary 4 in 3 bits is going to be 1, 0, 0. So I'm going to put 1, 0, 0 to represent the value of 4 for green, and then turn the rest of my blue bits off. Okay, continuing to the right here, red again is completely off. Now I want the value of 5 for green. So in binary, that's going to be 1, 0, 1. And then we're going to turn blue off. And then going again, the next green value is going to be 6. So in binary, that is going to be 1, 1, 0. And then we'll turn the blues off. And then finally, as I get to the last value of green, I want it to be the maximum value, which is going to be 1, 1, 1. And in base 10, that is 7. And there I see my brightest green. Now we're going to do the blue row. So again, we're going to start off with black. And this time, I know that my red and my green values are going to be completely off. So if I look at my model here, I know that those first 6 bits, meaning the 3 bits for red and the 3 bits for green, are going to be completely off, so all zeros. And then blue this time is what's going to be changing. So my first value of blue that is not 0 is going to be 1 in binary. In 3 bits of binary, that's 0, 0, 1. So I'm going to plug this one in next. And so now I see a very dark blue that might not even look so blue on your screen. And then going on to the next one, again, the red and greens are going to be off, and now I'm going to put binary 2, which is 0, 1, 0. And now I can see the blue has gotten a little brighter. And then continuing, again, red and green are off. Now I want binary 3, so that's going to be 0, 1, 1. And then for the next one, same thing, except now we want binary 4, which again is 1, 0, 0. And now I can see the blue getting much brighter now. And then the next value, I want blue to be 5, so that's going to be 1, 0, 1. And then for the next one, I want my blue to now be 6, so that's going to be 1, 1, 0. And then finally, I want blue to be at the max, which is 1, 1, 1, which is 7. All right, so now we've created our gradient for red, green, and blue, and we can move on. So in this one, we're going to practice sampling as we did in the previous lesson. This time, we are going to be sampling color pictures and trying to reproduce them to the best of our ability. And so, as we saw previously, when we use sampling, if we use kind of a lower sampling rate, it's not going to look exactly like the picture. In addition to that, if we don't use a high number of bits per color, we might not be able to match the exact color as well. So for my example, I'm going to go ahead and select this image and have it up on the screen while I work. So again, do not worry if, as we're doing this, yours does not match exactly, because we're using a limited number of samples and we are using a limited color palette. We can adjust the amount of samples that we take, and we can also adjust the number of colors we have access to. But for the purpose of this project, we're going to use a relatively low sample rate and a relatively low number of colors, because otherwise it would take a really long time to do. The main thing is to kind of get the idea of how colors are represented in binary and kind of acting like the computer in terms of digitizing an image. So I'm going to reset this. And right away, your first step is going to be setting your width and your height for your image. So I would like to have this pretty close to what I see on my screen. So I already see, like, maybe I want to make this a little wider. So maybe I'll make my width 10. And it looks like it's actually not so much that it's going to get wider, it's just going to make more pixels. So maybe I'll do the width as 9. And really what's important is that the ratio, right, the width and the height kind of match what I see down here. So maybe I want to adjust this a bit. Maybe I want 8 high, and let's see if that's kind of like this shape. So that's more of a square. So maybe I want 4, maybe 5. And feel free to put in your own numbers as you see fit, but I'm trying to get kind of like the basic overall shape and aspect ratio that I see in this image here. And I think what I see now is, I think that's pretty good. It's a pretty good match. So now what I can begin to do is split up this picture into 10 pixels wide and 5 high. And it's not going to be perfect because I'm using this silly annotation tool, but at least we can have a really good idea. So I'm going to try my best to split this into rows of 5, and then split it into 9 or 10 different columns. And again, in a perfect world, these would be these pixels would be squares, but this is just to get the basic idea. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, awesome. That's pretty good. All right, so now what I want to do is I want to make a decision about each of these squares. So what I'm going to do is I'm going to take a screenshot of this and I'm going to pull that up now. Okay. So now I can see that, all of the squares up here are mostly pink. And then we have some variation here where we might have some lighter pink colors going to darker. And then down here we can see like some yellow creeping in and maybe kind of like a muted peach color throughout here and then maybe getting a little darker. Then we see some yellows and then a more vibrant yellow down here. So we're going to try really our best to match these colors as we see them. But again, it's not going to be exactly the same. So I think for this one, perhaps the 9 bits per pixel model is fine. So that means that we're going to have 3 bits per color. Okay, so that means that we have access to 64 different colors, which is pretty good for this exercise. So let's start with this first color here. And remember, in order to make this kind of magenta color, we want to combine red and blue. So what I'm going to start out with is I'm going to start off with my reds completely on and my blues completely on. And I'm going to turn my greens completely off. So for this first square, I'm going to put 1, 1, 1 for red completely on, 0, 0, 0 for my green, so green is completely off, and 1, 1, 1 for blue. And now I see that magenta color. And as I'm looking at it and I'm thinking maybe it's a little bright. So one thing I can kind of adjust is maybe reducing the amount of red and blue. And that's kind of making my color a little dark. So maybe what I want to experiment with is maybe increasing the amount of green just by a little bit, just to see what happens. And now I see the colors a little bit more matched to what I see on screen. It's not exact, but again, we only have access to 64 different colors, and so I think this is perhaps the best that we're going to get. And I think that this color is pretty well represented throughout each of these pixels, so what I'm going to do is I'm going to reuse that for each pixel in this row. Again, it's not going to look like the original because we don't have infinite amount of sampling or infinite amounts of color. So now if I click on readable format, that's going to lump everything together, but I already had it that way, so that's pretty good. And now what I'm going to do is I'm going to move to the next row, and actually it doesn't really matter if I move my cursor to the next line. The computer doesn't care, but I'm doing it for readability. So I'm going to start a new line for my next row, and now I see the color, at least starting on the left, going towards the middle, is a lot more muted. So what I'm going to do is I'm going to take that original magenta color and I'm actually going to split this up so that I can see my red bits separate from green and separate from blue. And now I'm going to experiment a little bit. So I know that I can get closer to white if I increase green all the way to 1, right? I know that's white. So I know that in order to lighten my color, I might want to add some more green. But I might not want to add a whole lot, or else it's going to get too close to white. So maybe I will put that amount of green, and that looks kind of close. I can also experiment with reducing the amount of blue to see how that works, and that looks a little bit closer. And that looks too orange, so I think I'll stick with that original color. That's pretty close. So I'm going to go ahead and copy the color that I've created here for the first 1, 2, 3, maybe for the first 3 or 4, because then it starts to darken a bit. So I think maybe I'll start darkening it a little bit more on this 4th one. And again, to darken, I want to get these values closer to 0. Remember, closer to 1 is going to be white. Closer to 0 is going to be closer to black. So if I want to darken stuff, I might want to reduce these values here. So we can try adding in a little bit more blue. And that looks a little bit more pink. And actually I want to reduce, so let's take away some blue. That's going to look orange, so let's keep that the same. Let's instead add in, we already have red to the max, so let's actually take away some green. So we see that darkens our pink color a little bit, and I think that's pretty good. Again, it's not going to look exactly the same, but close enough for the amount of colors and sampling that we have. So I'm going to copy that color probably 2 more times. And then I think what I want to do is I would like to put the darker colors here. So I'm going to get that darker pink from the top row, and I'm going to finish off the rest of these. And then maybe take a look at, if I want to change anything. So let's see, I've got my peachy color, and then I've got these lighter colors. And then I just noticed that I have this wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's go ahead and just change that up so that it matches. Alright, so now I'm going to go ahead and delete these extra colors here so that it matches up. Okay, there we go. So now I want to make sure that I have all this matching up. So maybe I think I want one more of this middle color. So that's going to be this value here, and I'll just copy that in. Alright, so that looks pretty good. Now down here, I think I have more of, this color on the left, this peachy color. So I'm going to go ahead and copy that value, and I'm going to copy that all the way through and see what that looks like. Let me separate them out. I think that's pretty close. There's some variation towards the bottom here, but I think for the most part that's the color that's represented all the way through in this line. So I think I'm going to leave it at that. And then as I go to the next value, or the next row, I'm now seeing a lot of yellow. So we're going to have to switch up our color scheme. So now, in order to make yellow, I know that I want to combine red and green. So let's start out with just a pure yellow, and then we'll adjust from there. So I'm going to do all red, all green, and then blue all the way off. So that's a pretty bright yellow, and it's not necessarily a perfect match, but we can adjust. So let's first try maybe adding in some blue and see what effect that has. I think that's going to make more of a muted yellow. Yeah, so for that first one, I think we have some like deep yellow as well. So maybe what we'll do is we will increase the amount of blue, and that's, again, is going to make a muted yellow. So we're going to leave blue alone, and perhaps what we want to do is remove some green so we get closer to like an orangey color. And so now we see that kind of like darker yellow that I see down here, but maybe we'll add in some blue and see what happens. Not necessarily liking what I see. It might be closer to what's down here. Again, this is just about experimenting and seeing the impact on colors. So of course that's going to make it more green because we're taking away some red. So that's definitely a lot more orange. So I think I like this color. It's pretty close. Again, maybe I'll experiment with that blue. I think I'll just keep it like this. And you might be able to find a better color. Again, I'm not concerned so much about matching, I'm just getting the basic idea of how to represent these colors. So I think I'll stick with this color. And then I'm going to copy these all the way through, and then all the way through on this row, and kind of modify as I go. Okay, so I see kind of like that peach color kind of sneak in through like on these last two, so I think maybe I'll erase these last two values and grab my peach color. And again, you know, doesn't look exactly like what I see up here, but we've got the basic idea using, you know, this low sampling rate. And then finally down here we have this kind of deeper yellow than what we saw up here. So what I'm going to do is I'm going to take this yellow that we had here, and now I'm going to experiment with the blue values to see what I can do. And I think that's too light. I think I'm going to add in a little blue here, and then let's see what happens when I reduce green. So that's too much. So that's really close to the color that I have up at the top, which is fine because that's kind of what the dominant color of these three were. And I think I'm just going to copy those. So it's slightly a little bit lighter in color. Not by much, you can barely see it if you can at all. But if I look at this side by side, given that the amount of samples that we had, that's a pretty close match. Considering, you know, the amount of colors that we have and the sampling rate. If we bear in mind kind of how well we depicted the goose in the last lesson with a limited number of samples. So once we're done here, we can click Finish. And now we're going to look at these multiple choice questions and I believe a check for understanding question. So in this question, it asks which statement about analog and digital images are true. So analog images have infinite amount of data. So you can think of pictures that were taken with analog cameras, not digital cameras. You can think of things in the real world like paintings and stuff like that. They all have infinite data, meaning that there's infinite number of colors, and you can kind of think of it as an infinite number of pixels as well, although analog pictures don't really have pixels. Digital images break things up into those squares called pixels. So you have finite numbers of samples, meaning finite number of pixels, which is why, you know, you see kind of lower resolution images start looking a little blocky because the pixels are very large. And you have a finite number of colors as well, so the colors might not match up perfectly with the original analog image. So let's see, which statement is true here? With advances in technology, digital images look exactly like analog images they represent. So, I mean, I'm not really sure if they're saying like eventually. Digital images are always going to have finite amount of data. There might reach a threshold where we can't tell the difference, but it's always going to be have less quality and have less data than the analog, the original analog image. So it's not going to look exactly like the analog image that they represent, at least conceptually. To human eyes, maybe it'll look exactly because we can't see with infinite precision, but for this one I'm going to put question mark and we'll look at the other options. So the next one says sampling an analog image more frequently produces a digital image with better representation. So again, analog. An analog image is the one with infinite amount of detail and data. If we sample an original image more frequently, meaning we have more pixels, smaller pixels like this, yes, that does mean that there's going to be better representation because we're going to get a more precise representation. So I'm going to say that's true, but let's look at our other options first. Analog images come from data that is measured at regular intervals. So this is actually the definition of digital. Anything that is digital. Because things that are digital are represented in numbers like binary. So this is no, because that's the definition of a digital image, not an analog image. And then this one says digital images come from data that is measured continuously. And so this is actually the definition of analog. So they kind of reverse the definitions here. So we're going to say that this is false as well. So if I look at all these answer options collectively, I'm going to say that this is the best answer. This one is iffy because the images might look exactly the same as the analog image to human eyes, because again, we can't see with infinite precision, but it's still going to be worse quality. Digital images are always going to be worse quality than the original analog images because digital images have finite data. They are measured at regular intervals, and analog images have infinite data, that they have continuous information. So I'm going to select this answer, and we're going to submit, and we're going to celebrate because I got it correct. And then in this last question, we are asked to describe the process of sampling. So the process of sampling RGB pixels and binary sequences, how do they work together to display a digital color image? So let's think about this. So we have sampling, which means we split up an image into finite pieces, these little squares called pixels. And we can use the RGB model to assign a certain number of bits per pixel. So bits per pixel to represent colors, right? Using our RGB model. And then we are using binary sequences to actually represent those color values. So for instance, 001 in an RGB model where we're using 1 bit per color would represent the color blue. So let's try to put these concepts all together into an answer. So I can say that the process of sampling using RGB pixels and as well as, well, I'll say and using binary sequences work together to display a color image because we can split up an analog picture into a finite number of squares called pixels and use the RGB model to assign binary values to each pixel that determines the color of each pixel. So again, we're kind of using all three of these kind of vocabulary concepts to explain how color images are represented on a computer. So we take in the idea of sampling, which is making continuous information, continuous visual information of a picture of something in the real world, or even something in the real world, and then splitting that up into a countable number of squares called pixels, and then making a decision on what color value should each square be, and then assigning that square a value, a binary value that uses the RGB model to encode the amount of red, green, and blue to produce a color. So that's kind of like summarizing what I put here. And once you're done with this, be sure to click Submit, and then go back to your Google Classroom, and on this assignment in Google Classroom, you're going to click Submit as finished so that I know to grade it.